This video tutorial presents a generic experimental procedure. Please consult your class notes for term-specific instructions. The lab setup for this experiment consists of a DC power supply and a custom motor fixture. The motor fixture consists of a brushed DC motor with an integrated tachometer to measure shaft speed. A flywheel provides an inertial mass. A bicycle light generator can be toggled to apply an additional load to the motor. Turn on the DC power supply using the front switch. On your desktop, open the X95 shortcut folder and select Motor Control CDAC. LabVIEW may take a moment to load. Once the program opens, navigate to the Configuration tab. The sampling rate defaults to 200 Hz, but may be edited along with the allotted time for the motor to spin up to speed and back down, which defines the overall test duration. Here's a simple open-loop block diagram where the input voltage causes the motor to output a response by rotating. Your objective is to characterize the motor response by determining the motor and time constant. Start LabVIEW and select the Open Loop Control tab. For this example, the input voltage is set to 10 volts. Click the green Take Data button to initiate a test. As a default, the motor will spin up for 3 seconds, then down for 2. After the test, click the Save Data button to save the data to your desktop as a comma delimited text file. Here's an example of a data file opened in Notepad. Key settings are displayed in the header. All the time-dependent variables are listed in columns, which may be imported into MATLAB or Excel for analysis. Repeat the test multiple times while varying voltage up to 20 volts. Be sure to save the data file after each run. Plot the steady-state speed as a function of input voltage to determine the open-loop system gain. Then import the data into Excel or MATLAB to determine the settling time and time constant. Let's take a look at the open loop response when the load changes. Flip the lever to engage the bicycle generator and light. Now repeat all the previous tests to determine the open loop system gain under loaded conditions. When finished, gently retract the generator. The electrical resistance of the motor can be experimentally determined. Using the system model, sum the voltages in the circuit. Notice that if motor speed is held at 0, we can isolate the resistance. Wedge the pink eraser to lock the flywheel. In LabVIEW, set the open loop voltage to avoid current saturation and run the test. Multiple voltage settings are encouraged. Be sure to save your data afterwards. Now let's look at a simple closed-loop proportional controller, or P controller. Target speed is the primary input. You'll need to determine the optimal proportional gain for the system. In LabVIEW, select the tab labeled Closed-Loop P Control. There are 2 fields to set the proportional gain and target speed. As before, click the Take Data button to start the test. Afterwards, save your data using a descriptive file name. Vary the proportional gain and note the trade-off between steady-state error and unsteady oscillation, which is inherent with a P controller. Depending on the instructor, you may investigate the benefits of a full PID controller. As you've already seen, the proportional gain influences the rise time, but yields steady-state error. The integral term can eliminate this steady-state error, but can also introduce overshoot. The derivative term mitigates the overshoot caused by the P and I terms and reduces settling time. In LabVIEW, select the PID Control tab. There are multiple fields to enter the target speed along with the P, I, and D gains. The default values should be in the ballpark, but you're encouraged to explore the effects of the various gains. Once the controller is tuned and working pretty good, try running the motor with the bicycle generator. How does the controller perform now? Your instructor may have you investigate using a ramp input function on motor response, which may be selected in the configuration panel. The ramp time dictates the time to attain the target voltage or speed. All previous experiments may be repeated using the ramp function. Remember to save your data before leaving the lab today.